Okay, we're going to change a little bit here. We've been talking about volume recently, and now we're going to be talking about something known as the average value of a function. When you're finding averages, you kind of know how to do that. If I wanted to know what the average age of students in this course was, I would add all their ages up, right? And then divide by the total number of people, right? So that's the average, or more specifically what we call the arithmetic mean is the average that we're thinking about. But what about if you're trying to find the average speed of a vehicle over a course of a trip? There, the speed is not a discrete value. It's not like you can, I mean, you could sample your speed at certain times, but you are continuously changing your speed. There's not a finite number of times that you can sample in an interval, say for a 3-hour trip. I mean, I guess you can measure the speed maybe every second of that trip, but maybe you could do it every millisecond, and then every 1/1000th of a second, and so on. And same thing with things like average temperature, quantities that are continuous in nature. How do we find those average values? Well, I'm not going to derive how this comes about, but we can set this up and show that the average value could be calculated this way. Kind of makes sense though, because the integral here from a to b, right, this is a summation process, isn't it? We're finding area. This is like the adding all the values up, so to speak, right? And then what we're dividing by essentially b minus a, the length of this interval. So that's kind of like the dividing by the total number in a way. Well, this is how we define the average value. Probably the best way to think about it is with this mean value theorem for integrals. We have a mean value theorem for derivatives that we used when we were proving the fundamental theorem of calculus part 1. Hopefully you remember we recalled that from calculus 1. But we have a mean value theorem from integrals, and this says if the function f is continuous on a closed interval, then there exists a value of c in this interval such that f of c is equal to what? This, which is what? The average value of the function. Sometimes the average value is, again, written that way. And another way of rewriting this statement then is to say that there is some value f of c, and if I multiply both sides of this equation by b minus a, so times b minus a equals the integral from a to b f of x dx. And this is the way to think about that average value, right? And so what we're saying then is if I were to graph, let's say, a function on the interval from a to b, and let's just sketch a possible graph of a function here. Maybe it looks like that, nice continuous function. And so let's okay, from a to b. Now, we can talk about this integral over here. We know that that's equal to area under the red curve, right, and above the x-axis, right? The way I've got it drawn, it's going to be positive area. But then we also have this average value. So what is the average value? Well, let's suppose the average value of this is about right here. So what I'm going to guesstimate, and I'll explain why I think it's about here. Right. Average value. Draw a vertical line at that average value, okay? And you can see, first of all, the mean value theorem tells us that there's at least one value of c on this interval such that the value function is equal to the average value. And you can see it certainly, for instance, right here. There's one value, right, of c at least. And there may be more than one, but here's certainly one. Right, so f of c is equal to the average value of the function. Now, so how did I know the average value is there? Well, this tells me that this f of c, which is going to be equal to the average value, right? Right, this is the average value of the function, so f of c is equal to that average value. And what we're saying is if I take that average value and multiply it by b minus a, which is the length of this interval, that's going to be equal to the area under the curve, right, that I've drawn in purple. So what does this quantity represent? Well, f average, that's the height, and b minus a is the width, if you will, of what? A rectangle that's under this green dashed line, right? Under this green dashed line. And so let me just sort of, right, so it's all that area, including that right there, right? And so the idea is the green shaded area is equal to the purple shaded area. And the idea is that I can sort of take some scissors and cut right along here, right? Take all this purple area that is above the green area, and I can shove it into this little patch right here, which is green area, but no purple area. And they will balance out. In other words, those areas are the same. So that's kind of a way to think about what the average value of the function is. So it's correspondingly the area under this horizontal line, which is the value of the average value of this function on the interval from a to b. The area under that curve, right, which is a rectangle, is equal to the area under the curve as we go from a to b. So that's the idea behind the average value. So let's take a look at some just computations now. Let's just find the average value for the sine function over the interval from a to b. And so by the definition, the average value is the integral, or first of all, 1 over b minus a times that integral. And b in this case is pi, and a is 0. So this is b minus a, integral from a is 0, sorry, to b, which is pi, of the function sine of x. Right. Of course, 1 over pi minus 0 is just 1 over pi. What's the antiderivative sine of x? That's negative cosine of x. And we're going to evaluate it at pi and at 0. So I've got negative cosine pi minus negative cosine of 0. Cosine of 0, of course, is equal to 1. Cosine of pi is equal to negative 1. So be careful here. I've got a negative times a negative, that's positive 1, minus a negative 1 is plus 1. 1 plus 1 is 2. So this whole thing is 2. It's just 2 over pi. That's the average value for the sine function over the interval from 0 to pi. So what does this mean? What does this mean? Well, again, I've drawn a graph of the sine function from 0 to pi. Pi is about 3.14, so there's pi, right? And so I know what this integral here represents. It's the area under this curve. But this average value of 2 divided by pi, pi is about 3.14, right? 2/3 is going to be a little less than, or 2 over pi is going to be a little less than 2/3, because I'm dividing by a bigger number than 3, right? Pi is a little bit bigger. So it's about 0.66 something, 65 or something like that. But it's up here somewhere. Here's 0.5, it's 0.6 somewhere. So there is the average value, 2 over pi. All right, and if I come across here, let's just draw that horizontal line all the way across, right? That's the average value. Then the area under this green line, which above the x-axis, this rectangular region, that area, is the same as the area under the sine function curve. That's the idea behind the average value of a function. Does that make sense? Hopefully it does. Okay. I guess we go all the way over to pi there. So this rectangular region here that I've boxed in is equal to the area under the curve of the sine function. Okay, let's do a couple more examples of what we can play around with this average value of a function. Just stick that average value definition up there. So if b is a number greater than 1, and if f of x equals 2x has an average value of 11, over this interval. Let's find this value b. Let's find this value b. So let's see what's going on here. So the average value of this function f of x over the interval from 1 to b, what will that be? That's 1 over, and notice the value of a is 1 and b is just b, so it's b minus a or b minus 1, the integral going from 1 to b of f of x, which is 2x dx, right? And this is the average value of this function over this interval, and it has an average value of 11, so this must be equal to 11. So I need to solve for b here. How do I do that? Well, first of all, I can use the fundamental theorem of calculus to evaluate this, right? What's the antiderivative of 2x? That's simply x squared, right? Evaluate the upper limit of b, lower limit of 1, which would be, of course, b squared minus 1 squared, which is 1. So I have b squared minus 1 squared times this, which is really b squared minus 1 over b minus 1, or divided by b minus 1. That must be 11. Okay, so how do I solve this equation for b? Well, be careful. Notice I can actually simplify it this way. B squared minus 1 factors is what? B plus 1 times b minus 1. It's the difference of squares. And do you see how we can simplify this down? B minus 1's cancel, and I'm just left with b plus 1 equals 11. Now I did lose the information that b, could be 1, but obviously it can't be 1 because we would be dividing by 0 here, and we wouldn't have an interval going from 1 to 1, right? And b has to be greater than 1, so we've been told that. Okay, but so I can cancel this common factor here, and so very easily I get b is what? Subtract 1 from both sides, b is 10. Okay, and I can confirm and check, right, by plugging back in. I can plug in b is 10 to make sure that this computes to 11. It's another way of checking. Okay, so the interval from 1 to 10 in this case would give you an average value of 11. Let's do one more. Let's find the c that's guaranteed in that mean value theorem for integrals. So if you remember, we're guaranteed, right, a value c in the interval from a to b, right, for any continuous function on that closed interval such that f of c is equal to the average value of the function. So let's see what this looks like. First of all, let's find the average value for this function on the interval from 4 to 9. So it's 1 over b minus a, that's 9 minus 4, integral from 4 to 9 of the square root of x, which I'm going to write as x to the 1/2. Right, that's the average value, the square root of x over the interval from 4 to 9. So this is what 9 minus 4 is 5. The antiderivative of x to the 1/2 is going to be add 1 to a half, 3/2, divided by 3/2 is the same as multiplying by 2/3. And we're evaluating this at 9 and at 4. So I've got 3 times 5, I've got 2/15. Let's pull that constant multiple out. And what do we have then? We evaluate x to the 3/2 at 9 and at 4 and subtract. So 9 to the 3/2 power minus 4 to the 3/2 power. So 3/2 power means what? Square root and then cube. Square root of 9 is 3. 3 cubed is 27. Square root of 4 is 2. 2 cubed is 8. And 27 minus 8 is 19. 19 times 2/5, 19 times 2 is 38/15. Okay, so there's the average value for this function. And what we're asked to find now is find the value c in this interval that's guaranteed by the mean value theorem such that what f of c is equal to this average value. So I want to find the value of c. So now I'm looking at what f of c being equal to 38/15. And so what is f of c? That would be the square root of c. And how do I solve for c? I square both sides, so c is 38/15 all squared. And that comes out to be 1,444 over 225 if you square both of those. And that's the value of C. Interestingly enough, that is guaranteed. In other words, f of this value, f of this C value, is equal to 38/15, which again is the average value of the function, the square root of x, on this interval. Okay. So again, playing around with the average value in different ways. So that's a very helpful way to define average value for continuous functions, right? If they're non-discrete, then we're able to talk about the average value. Okay, so we'll stop the video here, and we're going to continue looking at more volume problems in a little bit different setting, different way of looking at it in the next set of lectures.